This is EE 597 with Professor Krishnamachari on Wednesday, July 6, 2016.
Okay, so we can have the, can I have the document camera, please? Thanks. Maybe take that off the screen. I can just, could you have that removed from the back screen? Is that something you can control?
I'm sorry, do you want the instructor PC on the overhead camera?
Yeah, I don't want the PC on the wall behind me.
Okay.
I think he wants to.
Great, thanks. So the last class we were discussing graph coloring. And specifically we were doing that because it was a tool for allocating channels. And these could be time channels or frequency channels or codes in a CDMA setting to potentially interfering cells or links. So we're going to continue some of that discussion and wrap it up today. But I wanted to make sure I don't forget the main announcement for today, which is that your midterm exams are next week. So it's on Monday, July 11. The exam will be in class for the usual class hours, usual class duration. In other words, from 12:25 to 2 p.m. It is open notes, books, printouts. Anything on paper? They want to bring in, but no electronics. So cell phones, calculators, iPads. Okay, so there's no electronics, but you can bring in anything that's on paper. So you can bring in your notes, you can bring printouts of any documents that you think will be useful to you, but there's no bringing anything that's electronic. That's the limitation. Hopefully that's pretty clear. Okay. Related to that, we will do a brief review of topics to date in class, and TA will post sample midterm exams and problems online. Okay. But this is really important, but not the solutions. Partly because we do, over the years, reuse some of the midterm exam problems for assignments. I think it's unlikely I'll reuse one of the midterm problems for the midterm, but certainly we do, over time. In fact, you'll recognize a couple of the midterm problems from one of the previous years was on a homework assignment earlier. So we're not going to provide solutions. They're really there for you as a reference to understand the types of questions you'll be expected to answer. And if in trying to work through them, you feel there's certain concepts that were not clear to you, you can certainly ask for the TA's help with that. He does have office hours still this week and should be accessible. But I guess what we're not encouraging you to do is to have him work out the answers for you that you can just write down and then bring to the exam as well. So we really want you to maybe spend some time looking through them and thinking about how you would address some of the problems there. And you'll see the problems vary in difficulty. Some of them are a lot more challenging than others. I'll mention a little bit about the exam format, or let's say at least likely format, because I haven't written up the exam yet. But likely, I will follow the practice I've had in previous years, which is a series of short questions, or maybe there are definitions, or fill in the blanks, types of things. These are really meant to test your understanding of basics. And followed by an additional, typically it's like 3 or 4 calculation problems. And whatever that number is, if that number is n, let's call it n equals 3 or 4 calculation problems from which the best n minus 1 count. Okay? So it sort of builds in the possibility that you'll get stuck on one problem, but you'll solve the other remaining problems well. So it gives you a little bit of flexibility. If there's one particular topic for whatever reason, or the calculation, you had some errors that ended up cascading through it, this gives you a little bit of robustness to that failure. So it's sort of a little bit of forward error correction built into it. Having said that, the amount of time on the exam is not very long. It's only an hour and a half. So given that you want to focus on the problems you think you best understand first, so you spend as much time as possible on what you know, and then the time remaining you want to attack the hardest problem of the lot, right? So recommend working on what seems to you to be easiest first. Okay, so I think it's a pretty standard tip. The other recommendation for exam preparation is the following. Is to go over the sample problems and see if you can identify classes of problems. Okay, and what I mean by this is, given the course content of the course so far, we don't even have a textbook, right? So it's basically whatever you saw in the lectures and the homework assignments and the project, and this set of sample problems. There's really only a finite set of ideas that I can ask you about. And one way to be really prepared for an exam is to have a full understanding of what those set of ideas are, what those set of concepts are. And you can try and reverse engineer that from the set of sample problems. So all of the problems that I posted are problems that I came up with, right? I'm not taking them from somewhere else. and I can only come up with problems that relate to things that I've taught about. And the number of things I've taught about are not infinitely many. There's a very small set of them. And if you can identify what those are, and for each one of them, you can then focus your preparation and understanding what are the basic tools and concepts you would need to know, what are the calculations you should go through and become familiar with. You'll also see that the problems require you sometimes to take something we discussed in class or saw in a homework, but with a little bit of a twist that requires you to sort of think freshly about the problem, right? So it's not just a blind repetition of what we saw. So it's rarely just, here was the calculation, I just repeated and changed a number. Generally, there's a little bit of thinking involved. But if you can at least identify the classes of problems and what you need to be able to understand those, you'll probably be in a much better position. I have to say this was something I figured out the very last semester I ever took a class, which was, I was in my PhD. I finally realized how to prepare for exams, and it was the only exam I had left. And after I was done with it, I had no more exams. But this strategy of really thinking about, from the instructor's perspective, what are the possible questions they could even ask, turns out to be very helpful because it immediately gets you to focus on how to prepare for it. So you'll see very, very quickly that there weren't that many types of questions even that there are. All right. So I will spend some time in today's class kind of going over concepts we've covered in the class till now, but let me kind of wrap up some of our discussion on graph coloring. So let's kind of recap how we got to graph coloring. As we were looking at sort of in cellular networks, we said that if you sort of look at traditional models of an ideal cellular network, that you kind of have this nice hexagonal type of structure that's often used to describe what the cells are, and that in these types of regular geometries, you can kind of create patterns of use of frequencies or channels in such a way that you can reuse the same channel at another cell that's sufficiently far away. So if, for example, I call ABC sort of 3 sets of channels, I can choose these sets of channels in the cells in such a way that they never repeat in any neighboring cell. So this is a particular, what they call reuse pattern. And basically the thing that we're ensuring here ensures that nearby cells or neighboring cells do not have the same channels. And just to clarify what the problem would be, if you didn't satisfy this condition, imagine sort of 2 cells that are very close to each other. Here's the base station for one, here's the base station for another, and you have a user A for this base station and another mobile user B for this base station. And if they're very close to each other and you're using exactly the same, say, frequency channels, that the communication from this user to its base station would also interfere with the other base station, and likewise the transmissions from that base station to its users would interfere with this mobile user, and in both directions in the other pair as well, right? And so basically these cross-cell interference between base stations and mobile devices is what we're trying to reduce. And if we ensure that these 2 base stations that share the same spectral resource are far away from each other, then these cross gains will be sufficiently small, right? And as we've seen before, for example, when we talked about power control, so long as the cross gains are made smaller, then you can have the links operate successfully. Okay. And in fact, I even mentioned when we were describing that we use power control in cellular networks when what is being allocated are CDMA channels, but even there, really, if you want to reuse the same set of codes, you want to do that at base stations that are sufficiently far apart, precisely to reduce the interference between them. So we kind of started from this, but then we said, this particular picture of cellular networks where everything is a hexagon is really an idealization. Things in reality are not this clean. What you will have is some, blob of cells, which the geometry of these cells might be a function of, right? So sort of this is ideal, but reality looks more like irregular cell shapes. Right? I don't know if there's a good example I can find. Yeah, most cellular providers are very careful to not provide detailed cell maps. They won't tell you exactly where their base stations are and what the coverage looks like. So there isn't really a good image of that we can look at. But certainly, these are because of propagation effects. As well as cell placement constraints or base station placement constraints. Okay, as well as power levels, transmit power levels. And sometimes the same network might use different pieces of equipment from different vendors or different equipments from the same vendor that have different maximum transmit power levels. And because of that, what the actual cell looks like in different parts of the city might be quite different, sometimes on purpose. So for example, intuitively you can see that if my cells were smaller, I could start reusing the same spectrum over a smaller physical distance, which means that I can have more capacity if my cells are smaller to some extent. Okay. So for example, in a very highly urban downtown environment, the cells are typically a lot smaller than if you're in some rural area where a single cell can serve the 30-odd users you might find within a kilometer of the base station. But in a city, maybe those cells are down to hundreds of meters to be able to pack in more users in each cell. And also to match user traffic. Okay. So the reality is things are not going to be very regular, and we still want to identify sets of channels to allocate to each of the cells so that there is no interference between nearby cells. And so the graph coloring approach can be used if we first abstract cells and their interference relationships in the form of a graph. Right, which is a collection of two sets, vertices and edges, where the vertices in this case basically correspond to cells, and edges are present between cells that interfere with each other. Okay. So once you're given any graph, you've already abstracted away the spatial geometry of the cells and the interference relationship in the form of this graph, right? So a graph is a very simple mathematical abstraction, and in many networking applications we use them for everything from routing to channel allocation in this case, to creating spanning trees, to creating subnetworks, to identifying the capacity of a network. So a lot of uses for graphs in networking, and certainly you've seen some of them before. Specifically in this context, the graph coloring problem says that given this graph find the smallest number of colors such that each vertex gets a color different from its neighbors. And we, so specifically, this is sometimes called vertex coloring. Okay. And one fact about this particular graph problem is that it's an NP-hard problem, which essentially boils down to the fact that in general, no exact algorithm that is tractable exists. Okay? And what we mean by tractable or efficient is that it would run relatively fast even for large graph instances, and specifically in computer science, that boundary has to do with, does your algorithm take exponential time to run in the worst case, or does it take polynomial time to run in the worst case? And we said that, so you can find an algorithm that will always find the best answer, the correct answer, quickly for any graph, but you can certainly relax this assumption and say, can I find an algorithm that runs fast and most of the time gives me a good solution, or often gives me a good solution in practice, right? So that's something we can ask. And an example of such an algorithm for graph coloring that we use that is often used is called the greedy vertex degree ordering. Heuristic. So we talked about it last time. I won't write it again. The idea was you simply sort every node in the graph in decreasing order of its degree. And if there are ties, you can break them arbitrarily. And all we're doing is you start with the very first node on that list and you allocate it the earliest possible color. And by possible, we mean that it has not been allocated to any of the neighbors so far. And you just keep doing that iteratively. All of the nodes will get colors that are guaranteed not to be the same color as its neighbors, right? So it certainly matches the required constraint for graph coloring. The only question is, does the number of colors you end up getting used, is that actually an optimal coloring or not? In general, there's no guarantee that for every graph you will produce an optimal coloring. In practice, it turns out that for many graphs that we encounter in practice, it does give us, if not the optimal, but near optimal solutions. So not guaranteed to always. But works well in practice. Other algorithms and heuristics also exist for this problem. For example, there is a very nice optimization tool called simulated annealing. There are other algorithms like genetic algorithms that people have used, etc. And if time permits, one of these days I would like to talk about simulated annealing, and maybe on a related note even briefly about genetic algorithms, because these are algorithms that can be very easily fitted to virtually any optimization problem. And I've often felt, I first encountered them when I was in grad school myself, that they should just be in the toolbox of every engineer, because you never know when you encounter an optimization problem, and being able to write or use a simulated annealing solver to solve your problem is a very big capability, because it's almost limitless in its potential. It can be applied to virtually any optimization problem an engineer might encounter. So the problems might be really, really hard, but you can always come up with a heuristic based on simulated annealing. And many practical problems, it tends to show very good results. So I will, time permitting, touch on simulated annealing in a little bit. So you have this heuristic, and certainly we looked at how we could apply it for that cellular problem. Graph coloring is applicable, and this is the point we were making towards the end of the last class, to other channel allocation problems as well. Okay, and a big example of that is channel allocation for links in multi-hop wireless networks. So let's kind of take an example of that. Okay, so maybe I have some network that looks like this, and this is an example of what I'm calling a multi-hop wireless network. And what I mean by drawing this picture is that each node in here is a wireless device, and these two nodes are talking to each other, or sending packets to each other. These two nodes are sending packets to each other. These two nodes are sending packets to each other, and so on. So one thing to be aware of is that most wireless networks that we use in our lives today are not multi-hop wireless networks, right? So cellular networks, for instance, are not multi-hop wireless. They're typically just a single hop wireless from your cell phone to the nearest base station, and the base station is wired. So it's only that radio interface layer of the cellular network that's typically wireless. In some cases, particularly in remote areas, the cell tower might have a backhaul microwave link that connects it to some other access or infrastructure point, but that's more of a special case and not really the norm. Other networks we encounter in our daily lives, Bluetooth, it's just a link between, for example, your phone and your car Bluetooth system. If you look at Wi-Fi, it's typically a direct link from your laptop to or phone to the access point. So these are all single hop wireless networks, right? So the majority of wireless networks we encounter are not multi-hop. But examples of multi-hop networks are what are called mesh networks. And we'll look at and maybe see some examples of mesh networks from the real world. But for example, there are community broadband wireless networks deployed in Boston that are mesh networks. So they have a bunch of access points that are not only directly serve customers, but also act as relays for other access points. And so you can kind of imagine that there's maybe a point in the city that you have a wired high bandwidth connection, and the data that's going from these nodes is going to some intermediate access point, which forwards its data to another relay access point, which forwards its data to another relay access point, and then eventually gets to the whatever the infrastructure node is. So in this case, there's sort of relaying happening as well, not just direct link. Mesh networks are often deployed in hotels, if you have, or airports, if you have a large collection of access points that you're deploying. Maybe not all of them have a direct Ethernet connection to the internet, but are actually some of the access points are relaying the traffic of other access points to get them to the final destination. Other examples of multi-hop wireless networks that we encounter, I think I mentioned last time, some of the smart metering systems for parking are starting to use these types of multi-hop networks, and sometimes they go under the category of wireless sensor networks, or sometimes low power wireless networks. And while mesh networks are typically 802.11 based, some of these networks use other standards such as IEEE 802.15.4. And in fact, here at USC, we maintain for many years now, close to 10 years coming up to, one of the earliest multi-hop low-power wireless network testbed anywhere in the world. So there's about 100 low-power wireless devices in the false ceiling in the 3rd and 4th floor of the RTH building. And it's a network we call TutorNet. It's in the RTH of the Tutor building. That has been used as an experimental testbed for protocol development, empirical evaluation, and so on. But it's sort of meant to be a testbed for developing software, testing it out, and then putting it for real applications out there. So later in the course, I'm hoping to spend some time describing these types of emerging new networks or next-generation networks. Other commonly known multi-hop networks include something called mobile ad hoc networks, which sometimes go by the name of manets or manettes. And these are typically networks that are used for more tactical type of applications, maybe firefighters that are doing some kind of a rescue mission. They're carrying radios with them in the environment, and the radios are able to not only talk to, are basically able to talk to other firefighters in range, and their radios might be able to then further forward the information that they're getting to other devices in range. So this may be a sort of a network of a whole bunch of people moving around with radios that can now communicate effectively end-to-end with each other. But they're sort of mobile in that the relays themselves might be moving around. They're actually people. Then that could be an example of that. So these are more, let's say, less commonly encountered in our lives, but they're certainly there and they're growing in numbers. So in the context of these types of multi-hop networks, you might want to allocate channels to your links. For example, the 802.15.4 standard provides for roughly 16 channels, depending on which country you're operating in. There's slightly different regulations and open and available spectra, but roughly speaking, there's about 16 channels in the 2.4 gigahertz range. And you can then potentially allocate different frequencies to different links. And one reason you might want to do that is that you can operate these links simultaneously then, without any worry about interference. And so if you have some rules for determining which links are interfering with each other, you could do that based directly on measurements, or you can have a model that says that so long as these links don't share any common links, they are able to operate simultaneously. You can then identify which pairs of links might interfere with each other. So let's what we're going to do is we're going to number the links in here. So I'm going to call these links, for example, I'm going to call this L1, L2, L3, L4, L5, L6, L7. So in this picture, I have sort of 10 different links in my network. And if I want to allocate, basically, imagine I want to allocate sort of different frequencies to these links in such a way that any two links that interfere with each other should not get the same frequency. So that's something that I might be interested in doing. One reason here that we might want to minimize the number of frequencies is that not all frequencies are going to be good to begin with. So I have 16 possible frequencies I can use, but many of these frequencies might actually interfere with Wi-Fi. Okay. In fact, let me even take a second to kind of show you or motivate some of our discussion here. Actually, could I have the PC here projected on the screen, please? And on the for the remote viewers. Okay. So I mentioned that we have here at USC, so this is the Ronald Tudor Hall. And this is the 4th floor of the Tudor Hall specifically. And these pictures on the left and right show the exact same network as the same set of devices. They're deployed in the false ceiling of the 4th floor. This room over here is where my group's lab is located. This is like a hallway down RTH It's also where your TA is sitting, somewhere in here. And these are some of the offices and labs on the 4th floor. And so in the ceiling above these offices and labs and hallways, there are, on the order of about 45 or so nodes on this floor and another 50-odd nodes on the floor below. So there's a total of 100 nodes in the network. This is just the 4th floor. And what it's showing is these radios are all operating using the IEEE 82.15.4 standard, and we've set the power level of the radios, in this case, to one of the lowest levels. So this is not the highest power they could be transmitting at. And when we transmit at this particular power, what we're measuring in this particular experiments that we're showing on the screen is we're trying to measure if a node sends a certain number of packets, how many of those packets get through. Okay? We'll talk in the next week about how you typically measure link quality at the link layer and above, and for the network layer and so on. And one metric that's very intuitive is called packet delivery ratio. So it's just what percentage of the packets that I send you do you hear, right? And so red links between pairs of nodes represent that they get between 50 to 90% of the packets that are sent to them. One reason we don't show links with even lower than 50 is that chances are you won't even think of them as neighbors. You probably are not going to send packets through them, or they may be so far apart that you hear nothing from them. So in that case, it's not a bad link. It's almost like not having a link at all. But between 50 to 90, that's sort of a range of values where it's sometimes very hard to figure out what is the, for periods of time, the links might look good and then they might look bad as the fading environment changes over time. So, but this is, averaged over a certain period of time, what the link qualities look like, and we're generating here kind of a time lapse of the link qualities over time. You can see the timestamp over here changing, and we're looking at exactly the same network on 2 different frequency channels. So we're looking at that network when we operate all of our links on channel 18 and when we operate all of our links on channel 26. And you can tell that in this example, channel 18, some of the links look good, and on channel 26, virtually all of the links look good, right? And this is because it turns out channel 26 is above the highest end of the Wi-Fi operating spectrum, whereas channel 18 happens to be more or less right in the middle of where Wi-Fi access points that might be operating on that floor are. But still, if you look carefully, interestingly, it seems like near the lab, this portion of the building, we don't see as much interference as we see at the other end of it. So if you kind of look at some snapshot here, you can see that this portion of the network still remains largely green, whereas there's a lot more red links over here. And maybe that's because there are access points over here that are interfering with the network much more so than over here. So the point of this was partly to illustrate how there could be a multi-hop wireless network, and this particular one's a research test bed, but one can deploy these types of networks for indoor applications ranging from asset tracking and people tracking to measuring environmental conditions, air quality monitoring, all kinds of uses people can come up with, industrial sensing, and so on. The point being that even though there are 16 channels total, and the channel is called 26, but the first channel is like 11, so it starts from 11 to 26. Not all of the channels are always good to use or available to use. So if I can color this mesh network in such a way that I allocate first of all, if I can allocate different channels to different links, I can prevent them from interfering with each other. If I give all of them the same channel, then they are subject to interference with each other. They have to use CSMA to resolve contention. The amount of throughput each link gets has to be reduced correspondingly. So I can improve my capacity if I could allocate more than one channel to this network, and the more channels I can put them into in such a way that they don't interfere with each other, the better. On the other hand, I may not have all the channels in the world. As I kind of rank order my channels in terms of their quality, some of the channels are really good, other channels are subject to a lot of interference. So the fewer channels I can use, the more likely it is that I can avoid the bad channels, right? So if I could find a graph coloring for this mesh network that only uses 3 channels, maybe I can find the 3 best channels that suffer the least interference from the other networks in that building, and that would be helpful to me. Right, and that would improve the reliability of my network. So even in this kind of motivating example, reducing the number of channels that I can use to create interference-free links is a good thing. Right. Can I get back to the document camera, please? yeah. So now I can kind of, ask this question. I have this network. I want to allocate to each of these links a frequency channel, and I want to avoid links that are interfering with each other from having the same channel, and I would like to also reduce the total number of channels possible. So if I formulate the problem in this way, then graph coloring is clearly what I want to do. So the first step would be to identify which links interfere with each other. So that's sort of step one. So one thing about this framework of graph coloring is that it only works on pairwise interference. So the only types of interference I can capture if I'm going to use graph coloring is that these two links interfere with each other. I can't capture the notion that I can't operate this link successfully if these three links are turned on at the same time, because that's not a pairwise notion. But I can specify these two links are not allowed to be on at the same time for a pair of links. Okay. So first I have to identify such a pair of links, and you might have some systematic way of going about it. You might take measurements to figure this out. But let's take a simple rule that says that if two links share either a common node or link, then we're going to say that they're going to interfere with each other. So for example, we could say that L1 and L2 interfere with each other because they share this node in common. So you can simultaneously be sending on this link as well as on this link. Or we could say that even this link L1 and L3 interfere with each other because maybe this node is transmitting to this node at the same time that this node is transmitting to this node, but because they have a common link with each other, that interference is going to be strong enough that the transmissions from here will interfere with the receptions here. So I can have some more systematic way of just looking at the topology and generating what the interference graph looks like. Okay. So whatever your procedure is for identifying those pair of links, we use this to construct what we call a conflict graph. That captures these interference patterns. Now, a key point is that in this graph, the vertices correspond to links in the original graph. Okay? So the conflict graph is not the communication graph. So this is the graph we started with, that's a communication graph. But a conflict graph has as nodes what are links in the communication graph. Right? So the nodes for the graph that we want to create maybe look like something like this. So if, for example, I say that there is interference between L1 and L2, I would put an edge there. If I say there's an interference between L1 and L3 because they share a common link, I would put an edge there. Similarly, I might put an edge between L1 and L4. Maybe between L3 and L4, L3 and L2, L3 and L5. So I'm just kind of trying to flesh this out. Maybe between L3 and L6 as well. Maybe. So I'm not sure if I'll get all of the possible interference links and relationships here, but at least you get the idea that we're basically placing links whenever we think two links might interfere. So for example, L4 over here and let's say L7 may not interfere with each other because they're sufficiently far apart, right? They don't have any common link or node between them, so these two will not have an edge. But maybe L4 and L6 have a common link L5 between them, so L4 and L6 might actually have that edge. Similarly, maybe L5 has an edge with 6, 7, and 8, but not with 9, because maybe 9 is just too far from it. Likewise, maybe L6 has links with 5, as well as some of these earlier ones. 7, 8, maybe even 9, but not 10. So, right. Link 10 might interfere with 7 and 8 and 9, but not any of the others. Okay. So I don't know if I captured every possible conflicting link here, but the point is that I can construct such a conflict graph, right? Whatever the rules are that I've described. So then what we do is color the conflict graph. So let's call this conflict graph H. Okay. And basically what we will get now are colors for each link that will guarantee that no links that interfere with each other get the same color, or frequencies in this case, which will have sort of, which will give us basically a minimum number of frequencies that we can allocate without interference. So one benefit might be reducing the number of frequencies might help us avoid bad channels. In other environments, reducing the number of colors might mean that I can fit more channels per color. So for example, maybe I only need 4 colors. I have 16 channels. What it might mean is that each color could correspond to 4 different channels. If my radios were able to utilize that diversity, either to increase their throughput or improve their reliability, that could be one of the ways in which I allocate my resources. Right? So in this particular case, the radios can't operate on more than 1 frequency at a time. It doesn't really add to their throughput, but you can imagine a different type of network where having more frequencies means you can simultaneously maybe do multi-user OFDM or use them as OFDM channels, subcarriers, to be able to run more higher throughput data through the network. So this graph coloring algorithm for allocating whether it's time channels or frequency channels to networks applies not only to that cellular setting, but also to multi-hop wireless networks. And in fact, we have been doing research in my group, and I might describe it, or at least point you at one of the papers that describes this research, where we are looking at a standard called IEEE 802.15.4e. And in particular, within that standard, there is a aspect of that standard known as TSCH, which stands for time-slotted channel hopping. And this is a standard for industrial wireless sensor networks or embedded networks, where the links are synchronized and allocated specific time slots and frequency channels. And in order to be more robust, have high throughput, and also low latency. Okay, so we've done research in my particular group on developing algorithms for figuring out which channels and which time slots to allocate to each link in order to get the best total throughput, in order to avoid interference, in order to have as little latency as possible between when data gets generated at some node and when it arrives at the final destination. So, so this is sort of an example of a particular class of wireless networks on which these ideas of graph coloring actually get applied in order to design algorithms and protocols for them. So I wanted to give you a bit of an example from the real world there. Okay, so that's really all I wanted to say about graph coloring. Notice that I didn't actually solve the coloring of the conflict graph, but the algorithm that we talked about last time, the greedy vertex degree ordering, could also be applied to figure out what's the minimum number of colors for this graph. It's the same idea. We would rank order each one of these nodes in terms of how many neighbors they have. We would start coloring and make sure we can repeat as soon as you can pick a color that does not show up in any of the neighbors. An earlier color, the better. And when you finish doing that for all 10 of these links, you'll be done with the coloring. So we haven't actually explicitly worked out the coloring. It might be a good exercise to try on your own. So let me take a step back now and wanted to do a little bit of a review of what we've covered in the class so far. Oh, before I do that, I do want to re-emphasize something we talked about last time in class, which was this relationship. And I think I might have used a different notation before for the clique number, so I'm going to use, I think I used psi before, but I think the common one is this. So this is called the chromatic number of a graph. This is called the maximum clique size. And this is the maximum degree. So this heuristic that we've been using, the greedy vertex degree ordering heuristic, is always guaranteed to return an answer that is upper bounded by the same bound that we are describing here. So you certainly can guarantee that whatever it ends up with is no more than this. And we know that that's an upper bound on the chromatic number of a graph. So the chromatic number of a graph is sort of the optimal solution to graph coloring, right? Which is the minimum number of colors that can be assigned feasibly. But there's a lower bound on this chromatic number that's sometimes useful in characterizing the optimality of the solution we get, and that lower bound is what's called the clique size. And we said cliques are basically fully connected subgraphs. So, and we saw an example of this last time, where either they could be just a single node, a link, a triangle, or 4 nodes that are all linked up with each other, or likewise, if you have 5 nodes, it would look something like this, and so on. So if you find that the graph you're trying to color has a clique, right? You look at all the cliques of the graph, as your graph is going to have at least a clique of size 2, that's trivial. But if you look at all of the cliques that it has, find the largest such clique, in other words, that has the most number of nodes. That number is guaranteed to be a lower bound on your graph coloring. You can never get away by coloring less than that. And the proof for that we talked about last time is very simple. Any set of colors you need to assign to these nodes must be different from each other. So you can't do less than that. And so if you have this heuristic at hand and it finds you a certain number of colors for that particular graph, you find the largest clique in that graph, you look at the number of that. If they happen to match, you're actually guaranteed for that particular graph that your heuristic found the optimal solution. If they don't match, there's no guarantee that it didn't find the optimal solution. It might still have found the optimal solution because the optimal solution is lower bounded by the clique size. It might be bigger than the clique size. It might be equal, it might be bigger. So your algorithm solution also will not be any smaller than this because it'll be feasible. But if it is equal, then you know it's optimal. If it's not equal, you can't tell if it's not equal because even the optimal was not equal, or is not equal because it, had some, was unable to find the optimal solution. Okay. So, this bound is something that comes in handy, at least on the lower end of it, to help us characterize how well the algorithm might have performed. Okay, so kind of a review of the class so far. Really, the course broadly is designed bottom up. We're starting from the physical layer, to the medium access and link layer, and then going up to the network layer and transport layer, and eventually if we can make it all the way up to the application layer. So far in the course, up to the midterm, we've really focused on the file layer and the MAC/link layer. Right? In the context of the physical layer, the kinds of topics we covered, started by just talking about various digital modulation schemes. So this is where we were discussing basically constellation diagrams. One of the concepts that we picked up from there was the notion of a power, throughput, and error trade-off. You can think of the power as directly affecting the SNR. And certainly one place where we saw this was as you increase the modulation rate, then your throughput will go up because you have a higher constellation. You're able to fit more bits per symbol. But as you pack in, if you have the same SNR and you're packing in more elements of the constellation, then you're squeezing them closer to each other, which means that you're more likely to make mistakes between symbols. So you're increasing the error rate. So you get that throughput benefit, but at the risk of error rate. Likewise, the power and error rate trade-off is very clear. As you increase the power, your error rate drops because the SNR is getting better. Typically, when we analyze any modulation scheme, the bit error rate versus the SNR curve is exactly doing that. The rate is fixed, the throughput is fixed, but it's telling us that if we want the error rate to drop, we must increase the power. Okay. And finally, for many systems, if you have the ability to switch between modulation schemes, what you might want to do is to not affect the error rate, so keep the error rate bounded by some number, and you want to change your throughput. You want to get higher and higher throughput, but the only way you can do that if the SNR is above a certain level, right? And so kind of the picture to keep in mind for you is that you might imagine there's a bunch of these curves. As you move to the right for bit error rate versus SNR, as you move to the right, this is sort of higher throughput or higher rate constellations. So if I really have a bound that I want to meet on my bit error rate, the only way for me to get to higher throughput is to have a higher SNR. Okay, and there was a homework problem in which you saw how the wireless LAN systems can switch their throughput as a function of the SNR. They can choose which modulation scheme is being used by measuring the SNR. And so when you're closer to the access point, the link quality is good, the SNR is high, you get a high data rate. The farther away you go, the SNR drops, and it switches to a lower rate modulation scheme. When we talk about, for example, the sort of the Shannon capacity of channels, we say that the rate is proportional to log of 1 plus SNR, then this is also the kind of relationship we're referring to where really when you're describing something like this in a real system, the error rate is being kept fixed and you're showing the trade-off between throughput and power. Okay? And the key point here is that you have to increase power exponentially in order to get sort of increases in the rate. And that's why there's this log term in there, right? Which means that the SNR needed grows exponentially in the rate. So that's one reason why our wireless systems are fundamentally rate limited, is that in order to increase that data rate, Shannon's capacity system theorem tells us we can always do that by increasing the SNR, by increasing the power of the transmitter. But there's two problems. One is that in real systems, having exponentially large amounts of power is not feasible. Second, in really dense systems, we can't even reach the maximum power level in many cases because you might improve the SNR for a single link, but you might increase the interference to other links nearby. And so we typically have a lot of limitations on how high a power we can choose, and that affects the rate performance. So those are some very basic concepts we picked up from understanding how digital modulation schemes work. In some sense, some of these trade-offs are very generic. They're not even necessarily unique just to wireless, but it's really important because these core trade-offs prevent us from having a very high throughput wireless network with very low data rate, with very low energy consumption. We can have all three things at once. Right? So this is a very fundamental limitation we have to work around. And it's also one reason why we have so many wireless standards. Some wireless standards are focused on high data rate communication, but they can sacrifice the power consumption. They have an always-on system. It's a very capable device. Other applications, such as the Internet of Things, where you want to have your toaster, for example, or your little objects or smart objects in your environment have wireless capability on them. They're running on AA batteries. They don't have a lot of energy capability. They might need to operate at very low throughputs, right? Because without all of that transmit power, the range is going to be limited because of the SNR being too low at some point, and also because the SNR is relatively low, the throughput itself might have to be limited. So that's, depending on the application context, we might have different trade-offs that we're looking for in terms of power, throughput, and error. Okay. And as a consequence of that, we have a bunch of different standards, each addressing a slightly different trade-off. Okay. So that's something about the modulation schemes. We also talked about radio propagation. And we looked at a few different models. The simplest model is called simple path loss, which simply captures the fact that your received power that you receive at certain distance is typically scaled in some fashion like this. So what this is saying is that if D equals D0, so this is 1, then what you receive is K times what you transmitted, or sometimes called Kref. This term over here is called the path loss exponent. Okay, and in practice it's between 1 to 5, depending on the environment that you have. It might be lower than 2 if you have reflective surfaces. For example, when we take measurements in hallways, we often find in indoor environments with polished floors, very little furniture, we often find that the path loss exponent might even be below 2. And the more absorbing the structures in the environment are, the higher that exponent might get. In vacuum, it has to be 2 because the way the spherical radio wave propagates, the surface area is scaling inversely as the square of the distance. And any antenna might be capturing sort of a certain portion of that surface area that would scale correspondingly. So, and this D0 parameter is like a reference distance. And one thing to keep in mind is that typically this model is only valid for values of distances above the reference distance. Okay? Because if you take this model to an extreme, and in particular, to the minus eta means it's actually D0 over D to the eta. If D goes to 0, this term will just blow up on you to infinity, and you would end up at some point even receiving more than you transmitted, and that's clearly nonsensical. So it's only really meaningful in this regime where D is bigger than D0. Sometimes we lose sight of this, but that's a key observation about the model. This path loss model just captures sort of an average behavior. In practice, what we really encounter is fading. And the simplest way to model fading in an environment, first of all, why does fading happen? Is because of multipath reflections, absorption, right? Really, it's some of the material properties of the environment, etc. And the simplest models of fading is to model them as sort of an IID random variable. So you have a certain path loss, and then on top of that path loss, there's some statistical variation. Okay, and so then we have a model like this, where this is a fading random variable, and a typical model for this fading is a log normal distribution. And the way to understand a log normal distribution is that if you look at it in the log scale, it's a Gaussian. It's like a standard normal. I would say standard. It's a normal random variable. So if we look at this in the dB scale, we would see something like this. Let's say minus 10 eta log 10 of d over d0 plus dB scale, where this term is now a random variable that's distributed with some zero mean as well as a variance in the dB scale that is called the fading variance. So in this model, we typically would characterize the environment by defining what D0 is, defining what Kref is, defining eta, and defining the fading variance. So these are all parameters that describe my environment. Okay. We talked about more sophisticated models than a simple IID random variable. And in general, it could be any kind of random process, but other models that are used quite often but that sort of capture temporal correlation are discrete Markov models, and the simplest such model is just a two-state model. So simple two-state, what's called the Gilbert-Elliott model. Where we're just saying the channel is either in a good state or in a bad state, and this is a good abstraction, particularly for the link layer, where you don't care so much about the actual SNR or the RSS that you're getting, or the signal power that you're getting, but you just want to know, is the channel in a state that's above my SNR threshold or below my SNR threshold? So I define some threshold, and I say if it's to the right of it, it's in a good SNR state, and therefore I'm getting the packets, and below it, I'm not getting the packets. So that might be a type of link that I might want to model as a Markov chain. And here are parameters of the model. There's only really two independent parameters. If I define two of these numbers, the remaining can be figured out because they're simply one minus the other. So P01 is 1 minus P00 and vice versa. And you can do, with the Markov model, one benefit is that there's some predictability built in. I can ask questions like, if the channel is good now, how likely is it to be good at the next time step? Whereas with a pure IID fading environment, how good my channel right now is has no bearing on how good it's going to be the next time step that I'm going to be taking a measurement. It has no built-in notion of memory or correlation in the channel model. So this, depending on the application, can sometimes come in handy to model the time-varying nature of wireless channels. We talked about two metrics for fading channels. So if you have an AWGN channel, before we go there, so if you have an AWGN channel, a typical metric for how good it is to look at the bit error rate, right? So, there's some probability of bit error rate that's a function of the SNR. So you say, if you tell me what the SNR is, I can tell you what the probability of bit error rate. And that would be derived based on the constellation, based on the probability that you might mistake one symbol for another if the channel added noise to it. When you have a fading channel, the key thing that happens is that this SNR itself is not a known number, but a random variable. And so it's not even clear which probability of error you're referring to, because that SNR that's a function of is what's varying, potentially. And so we can talk about the expected bit error rate. And the expected bit error rate basically takes the expected value. So if this is a random variable, then the probability of bit error rate, or sorry, the probability of bit error, which is the bit error rate, is also a random variable. I can ask what is the expected value of that random variable, right? And so we can do that by using the fact that in general the expectation of a function of a random variable can be defined by, let's call it G, right? If you know the distribution of that random variable, you can compute its expectation. So in this case, the G that we're talking about is this bit error rate function. The X that we're talking about is the SNR. And so if we know the distribution of the SNR and we know what the bit error rate function is, which will depend on the modulation scheme, we can compute the expectation for that particular system, and that'll give us an expected bit error rate. So this is like saying, on average, how many of my bits do I lose, given the fact that sometimes the channel is good, sometimes the channel is bad. When the channel is good, I lose packets at this rate, or bits at this rate. When the channel is bad, I lose them at this rate. This is the average over all of those. The other metric is called probability of outage. And the probability of outage is simply the probability that the SNR falls below some threshold, right? So this is the random variable that we have describing our process, and this is some SNR threshold that's predefined. And why you might choose a particular threshold to be the predefined value is that maybe your application needs your bit error rate to be a certain value. And for that modulation scheme, that bit error rate corresponds to some particular threshold SNR. So if your channel SNR drops below that value, you're not going to get the packets. And so you might ask, how often does it happen on this channel that I'm unable to get my, in this case, I'm unable to get my, if it's a packet corresponding to a certain SNR threshold, how often does it happen that my SNR drops below this threshold? Okay. And so this can be defined also in terms of that SNR distribution as basically the probability that I fall below the outage threshold. Right, so this should be where this would have to do with the SNR distribution. SNR fading distribution. So the point is that if I know the threshold and I know the fading distribution, I can figure out the outage probability. Likewise, in the bit error rate case, I need to know both the fading distribution as well as the performance of my modulation scheme as a function of SNR. Here, there's also an implicit dependence on that function because that's how you would determine what the threshold should be, and we've talked about that. Other physical layer concepts that we really touched on relatively briefly are notions of Doppler spread and what we call, okay, so there's Doppler spread, there's delay spread. So in the case of delay spread, it's what's called coherence bandwidth. And with Doppler spread, it's what we call coherence time. Okay. One way to distinguish these sort of ways to characterize fading is really what this is about. The coherence time kind of tells you if a channel is good, how long is it before it turns bad, or if it's bad, how long before it turns good. Delay spread is about how echoey the environment is. How many different copies of the original message end up arriving and at what delays. Okay. And if you kind of look at their inverses or their duals in the other domain, so this is coherence time is a time concept, Doppler spread is a frequency concept, likewise delay spread is a time concept, and coherence bandwidth is a frequency concept, that they're sort of duals of each other. And this Doppler spread in coherence time has to do with whether we have slow or fast fading. Okay? And we say fast fading corresponds to low coherence time, high Doppler spread. And slow fading corresponds to high coherence time and low Doppler spread. And if I can give you a little bit of an intuition about what Doppler spread is doing, imagine that you were observing your received signals or the quality of the channel. Okay, let's think about the signal that we're receiving. Okay, so imagine that somebody's just transmitting a sinusoid, and it's going through this channel. And you have the source and the destination, and the source is moving. Okay? So even if it's sending a pure sine wave, the fact that it's moving means that the perceived frequency at the receiver is not going to be a pure sine wave, it's going to be varying. Okay? If it's moving away, you're going to see that the frequency will start to decrease. If it's moving towards you, you'll start to see that the frequency will start to increase. But in any case, you can kind of imagine that it's going to spread the perceived frequency across a range of values. That's Doppler spread. And the faster that movement is, the more of a spread you will see. Okay, so this velocity of the movement enters into how much spread you see. But this movement also affects the quality of the received signal in terms of how long does it take before the channel looks different because the frequencies are changing, right? And so in the context of an environment where there's mobility either of the source or the destination or of objects in the environment that the multipath reflections are coming out of, when any of these things are changing, you're going to see not only a high Doppler spread, you'll also see that the channel changes from being good to bad or from bad to good relatively quickly. Okay, so that's the aspect of the channel that's captured by Doppler spread and coherence time. And you know, one example I like to give is about the testbed even that we were mentioning earlier. If you measure the signal quality on that testbed at night, it stays virtually unchanging all through the night. And from the morning, once people start coming in, moving around that floor, because the nodes themselves are not moving on this test bed, they are fixed in the ceiling. But the movement of people around causes different amounts of reflection, time-varying reflections, and the signal quality and the SNRs on each of the channels starts changing pretty dramatically during the daytime. So what ends up happening in that particular network is that during the daytime it experiences fast fading, and at nighttime it experiences slow fading. So you have a link that's really bad at the beginning of the night, then all through the night it stays bad. Whereas during the daytime, because of all these time variations, the bad channels turn good relatively quickly, but then also will turn bad really quickly. So there's sort of this average channel that you end up observing over a short period of time. So fast fading is not always a bad thing. Sometimes it's a good thing because it means that you don't get stuck in deep fades, right? On the other hand, it's a bad thing because you always end up kind of seeing these average behaviors. Whereas if you have a network that's deployed, remote, statically deployed network, nothing is changing in the environment, you'll have a very slow fading environment. If at the moment of deployment and start of operation things were good, things are going to stay good for a while. So that's a stable environment. On the other hand, if some of the links were bad, they stay bad too. This other dimension of delay spread, again, I like to create some analogies to acoustic propagation, that the way sound propagates in caves and environments that are full of reflective walls is very different from the way sound propagates in an open field, right? And you've all observed that when you're in an environment that has a lot of echoes, that if somebody's talking very fast, it's very hard for you to understand. So you kind of almost instinctively start slowing down your rate of talking so that the echoes are not interfering with your own words. Okay, so that type of sort of interfering with your own symbols in the context of wireless communication is called inter-symbol interference. And this results if symbol duration is not large compared to the delay spread. And so when is the symbol duration small? It's when you're trying to do high data rate communication. And so generally, environments with high delay spread are a problem when you're trying to do high speed communication. Okay. And so increasingly, as we're driving some of our cellular networks and our wireless networks, wireless LANs to higher and higher data rates, delay spread and intersymbol interference starts to become more of a problem. One solution that's now become de facto, like the main way to deal with this, is to use OFDM. And the reason it's a solution is that it divides a single high rate stream into multiple low rate streams. And in these low rate streams or subcarriers, the symbol with large symbol duration. And these symbol durations can be made large enough that they're much larger than the delay spread, and so you don't end up seeing sort of smeared versions of the symbol causing interference with each other. Okay. And so if you look at the latest wireless LAN standards, Wi-Fi standards, as we're going higher and higher in data rates, they're starting to employ OFDM. Okay, just as cellular systems have done that as well. So the coherence bandwidth aspect of delay spread is a little bit less intuitive, but actually is what gives it the title of either flat or frequency selective fading, which is that if you kind of look at the frequency response of the channel, when you have a low delay spread, the frequency response is kind of flat across frequencies. You get the same gain at the receiver at different nearby frequencies. Whereas when you have a high delay spread, it turns out that the channel becomes very frequency selective. Changing the carrier frequency by a little bit can increase or decrease your gain of the channel dramatically. So that's, from a frequency perspective, what's happening to these channels. So there's a different class of techniques used to combat delay spread that are called channel equalization, where you increase the gain or decrease the gain at different frequency values to try and compensate for the distortions introduced in the channel. So this is sort of a completely different way of viewing what delay spread does to you. Personally, I have to say that as somebody who works largely at the higher layers of wireless networks, I've found conceptually it's enough for me to focus on the time domain aspects of these two fading environments. So thinking about the time scale over which the channel is changing, good or bad, is more helpful to me than thinking about the frequency spread. And likewise, when it comes to the delay spread, thinking about things in terms of symbol durations and the delay spread in terms of the the longest delay of the multi-path components that are showing up at the receiver, that's somehow more helpful to me to think about from a higher layer perspective. But certainly you should be aware that people in wireless communications look at these frequency perspectives as well. We briefly touched on spread spectrum, and the main thing to really take away is that there's two kinds of spread spectrum, direct sequence spread spectrum and frequency hopping spread spectrum. And both of these are used. Direct sequence spread spectrum systems show up even in things like cordless phones for many years. They have the benefit of allowing you to spread your data across a larger range of frequencies by using appropriate chip sequences. And by designing these sequences carefully, you can actually help to reduce a lot of the multipath components. So that's, in fact, one of the ways in which people can deal with delay spread as well. If you use direct sequence spread spectrum with carefully designed sequences and you allocate different sequences to different users, that's the basis of CDMA. So CDMA is sort of an application of direct sequence spread spectrum where different links are being given different sequences, and they're carefully designed, these sequences, so that different sequences don't interfere so much with each other. Frequency hop spread spectrum is used in Bluetooth in particular, and is a much simpler conceptually to understand. It's just you're sending your data on symbols on different frequencies at different times, and you're constantly hopping between these frequencies over time to give you some robustness to narrowband interference. We talked about MIMO, which is increasingly, we're going from single antennas to sort of multiple antennas at the sender and receiver. And sort of two sets of things we talked about in this context. One is we talked about something called maximum ratio combining and the idea of diversity, which is that if you have many different receivers, you can take what's received in each of these receivers, correct for the phase, and you can combine them. And in particular, if you combine each of the channels with a gain that's proportional to the received signal strength, you get the maximum SNR. So that was sort of an aspect of this. The other thing we pointed out that in general, if you have multiple transmit antennas, multiple receive antennas, you can use these degrees of freedom either to improve your diversity, which is to reduce your error rate, or to improve your throughput, which is to increase your gain, which is to increase your what's called a multiplexing gain. So this is sometimes described as the diversity multiplexing trade-off, and roughly speaking, sort of, improve throughput or error rates, okay, or some combination of these. And in fact, if you look at 802.11n, which is a 802.11 standard that has MIMO, there are different modes you can set your transmitter and receivers to that give you either improvement in throughput or improvement in reliability. We then talked about, I think this was most of what I wanted to touch on for the physical layer. I think we briefly talked about, techniques such as coding. I don't know what else those in the physical layer. But going beyond the physical layer, we got to MAC and link layer. I mean, I didn't spend a lot of time on coding. I just wanted you to be aware of this class of techniques that exists. But at the link layer is when we started talking about things like power control and allocation. And we, with respect to power allocation, we looked at allocating constrained power to parallel channels to maximize the sum rate, okay, or other functions of rate. So in one of the homework assignments, you also looked at some kind of an objective where the goal is for each channel to try and reach a certain rate as closely as possible. And this is the problem for which we developed the solution called water filling. But more generally, this was sort of applying the method of Lagrange multipliers to calculate the optimal power allocation. Okay, so certainly from the exam standpoint, I do expect that you thoroughly understand for the sum rate case how we derived it, but also for other objective functions, what's the methodology, how does it extend? And for the water filling solution itself, how does the power allocation vary to each of the channels as you increase the total power, as you, if you were to change some of the gains and so on. So really understanding this solution would be a good investment of your time. We talked about, one thing to keep in mind about one assumption here. So we assumed that the rate on the ith channel is proportional to log of 1 plus the power on that channel times the gain to noise ratio. When we say a statement like this, we're implicitly saying that we have, this implies an adaptive radio. What I mean by that is that the radio we're talking about must have the ability to switch modulation schemes. Otherwise, there's no way for you to convert power level to data rate improvement. And not all radios allow you to do that. So in particular, the radios that I mentioned, the 15.4 radios, they have a fixed data rate. You can't change the throughput. Doesn't matter how much transmit power they're throwing out from the radio antenna, it cannot be changed to a different modulation scheme. Okay?
Professor, it's your 5-minute warning.
Okay. So depending on the radio that you have, this assumption may not hold, right? In fact, when we talked about power control with independent links, where we sort of try to identify what's the power level that they can transmit at, so that they both satisfy that SINR for both of these links is above a threshold. In this case, when you talk about a threshold and you want the SINR to be above a threshold, here we're talking about a fixed rate radio. So here we're not translating improvements in SINR to higher data rate. We're just saying you want to make sure you're above a threshold, and you're happy if that happens. Because for whatever throughput you have, you just want to make sure you're getting a sufficiently low error rate. Okay. In the medium access context, we've talked about slotted aloha. You should familiarize yourself with both the homogeneous case, where the throughput analysis is everybody transmits with probability P, as well as the heterogeneous case, where everybody transmits with probability Pi. And in this case, we kind of describe a saturation throughput region. And we didn't explicitly derive, but we stated that one interesting condition that ends up happening for slotted aloha is that at the saturation throughput boundary, this condition is satisfied. Okay. We talked about P-persistent CSMA. And again, we also talked about sort of PI CSMA in that same vein. And in this case, the key idea is that you have these different time constants for the slot duration, the contention duration, and the successful packet duration, and the throughput ends up being a function of each of these parameters as well as the parameter for the transmission. And so, again, we derive sort of the throughput expressions for PCSMA, take these into account. And a big finding from regular slotted aloha is that the throughput is kind of, the maximum throughput is like 1 over E, doesn't matter how many users you have, but here the maximum throughput can tend to 1 as TS gets larger. Right? Specifically, TS over delta gets larger, your throughput can actually tend to close to 1 in CSMA. Again, there is a saturation throughput region for PI-CSMA, and there was a slightly more complicated expression that holds at the boundary of the CSMA saturation throughput. We talked about 82.11 CSMA, which was the whole Bianchi analysis, what that Markov chain looks like, and how analyzing that Markov chain gives you analytical expressions, which in the project you compared with the simulated curves, and hopefully you got results that were reasonably similar to what was in the paper. And then the last topic we've really touched on in the last class, and this one has to do with time or frequency scheduling using graph coloring. Okay, which of course, since we've just talked about it, I'm not going to review. But really, these are all the sets of things we've talked about in the class so far. As you go through the example problems, you should be able to find that how they relate to the topics we've talked about and what kind of skills you might need to be able to solve those problems on the exam on Monday. So good luck, and I will see you in class on Monday the 11th. No, it's explicitly the thing we're not doing. that's where either you have to rely on, I get it, I can see how this would work, or you should talk to the TA.
This concludes E597 with Professor Krishnamachari on Wednesday, July 6, 2016.